Our guest today is Wissam Kontar. He's a Ph.D. student at University of Wisconsin-Madison and working under supervision of Professor Soo-Young Ahn. He has done his bachelor's in engineering in civil engineering
Recording is
in
on.
American University of Beirut in Lebanon, and in and he has also a major in mathematics. So his his key focus, his research focus is on real-time performance analysis of interconnected transportation systems and microscopic traffic flow modeling and data-driven control of connected and uh, automated vehicles. So, Wissam,
Yeah,
please.
thanks. Thanks a lot. Thank you, Professor Levan, and thank you, Ravish, for your coordination. So I'm pleased to be here with you on this webinar series. So today our talk will be on this multi-class automated vehicles, the car following behavior and its applications for traffic dynamics. So to start with, let me first acknowledge our co-authors and collaborators. So our collaborators are from UMass Lowell, specifically Professor Danjua Chen's research group, and our co-authors are Tianan Lee, Anupam, Yangzhu, Professor Chen, and Professor An. So this is what I'm presenting today is a portion of the work that is pending for ISTT 24, and it's sponsored with the NSF Foundation. So a brief outline of what we're going to discuss today is a motivation for this multi-class automated vehicles problem, some empirical analysis on the car following behaviors using some real data, and we will delve into more in the control mechanisms and discuss really the car following behavior of two main controllers, the linear controller and the MPC model predictive controller. And then we'll delve into some predictive modeling for this car following behavior and finish with conclusions. So really, when we look at the bigger picture of this new traffic environment, so when we think about it in the previous sense, or the research that has been going on in the past decades, it has been mainly focused or influenced by two specific components, these traffic dynamics and the intelligent transportation systems. And these include all sort of things from sensing capabilities, transportation networks, intelligent signals, various forms of automations and adaptive control. But now what's coming into play is this new component here, which is basically the automated vehicles. And these vehicles have really been described as this disruptive technology, which can bring tremendous benefits to our systems from safety, from comfort, from stability, from throughput, and from all this beneficial stuff. But the main thing here that there's no free meal, as they say, and there we have this adding complexity, major complexity to our system. And this complexity can come from different ways, specifically from how these control algorithms are designed, especially from these auto companies that they implement various different control algorithms and they typically behave differently. So, and we have seen this actually within empirical analysis, and there has been recently some field data studies on ACC vehicles and other CAV vehicles like the Waymo, the Nissan, Ford stuff. So the main issue is that this link here is what we are interested in, is that the automated vehicles, they bring this new dimension of complexity, and it's driven by this variational in the control and the complexity in the behavior. So on this research will be focusing on this link here, and we want to understand how these variations in control dynamics, they impact that control models, they impact these traffic dynamics, and ultimately, we want to provide some insight on how these vehicles should be designed so that they are not just beneficial at an individual level, but at a system-wide level. So this idea of microscopic to macroscopic design. So then this understanding, this connection between these traffic dynamics and automated vehicles has a lot of challenges in it. And specifically, these challenges are between how can I integrate my automated vehicles inside my traffic system. And so the first set of challenges is that traffic systems in itself is a complex dynamic environment. So many influence factors, such as the varying demand-capacity relationships, road geometry, presence of traffic control, and all these different complex stuff. And what we are adding now is a new level of complexity that comes from AVs, which is we have different control paradigms, different control logics, So the behavior of the AV would behave differently depending on what objective in the control we are prioritizing, and we will see this throughout the talk. And then this kind of heterogeneity in the AVs can impact this traffic flow even for better or for worse, especially under traffic disturbances, which are very much common features in our systems, and we expect them. And another major challenge is that, so these control paradigms, linear controller, MPC, or whatever different controllers, they originate on this control theory or AI-based fields, and naturally they lack this direct traffic insight. So they sometimes can be a bit of a black box, and we cannot gain this direct insight into traffic. So they are microscopic in nature, and it's difficult to translate this behavior into, or scale up this behavior into traffic level behavior. So what we are interested in is then need a systematic analysis of the mechanics of car following behavior under different control paradigms in a way to better understand how they impact the traffic level and how do they behave in general. And this will give us some insights on how can we guide this design of AVs to have scale up or traffic level performance in mind. So some objectives of this talk, and with that in mind, objectives are really to characterize these car following behaviors under different control paradigms. And we want, in the same way, we want to investigate what are similarities, differences in car following behavior of between linear controller, predictive controller, and all these stuff. And then we want to elucidate how these actually work at the traffic dynamics and at the disturbance evolution. So mainly the question becomes here is that first we will focus on dynamic car following control. So what is the control logic, or what is the vehicle designed to do? And when we understand this, we will move into the physical mechanisms of the control. And the question here becomes, okay, so what drives this physical behavior? Or what are important parameters or important behaviors that govern my physical car following? And when we capture these two important concepts in mind, then we would have a bit of understanding of traffic impacts, and we say that, okay, what will happen at an aggregate level or when I have a combination of these vehicles together. So, and this especially is a loop type control where, okay, when I know all these behaviors, I can somehow guide my control, guide the control of my automated vehicle. So, an general overview of like this, the scope of this research, and what we are trying to do is that we were trying to so we have these different control paradigms, a linear controller, MPC, and AI controllers. So we're mainly focused on this talk on linear and MPC controllers. AI, we are currently studying them, but it's a work in progress. So, and then we want to reach this understanding on physical mechanisms. And to do so, we want to analyze the car following behavior. And in this component here, we run like different simulations representing various disturbance scenarios, different parameter settings. And then we simulate the trajectories and we approximate this dynamic car following behavior using the asymmetric behavior model, which is a physics-based car following model that extends the Newell's simplified car following model. And the AB model really here serves as a unifying framework to analyze the physical mechanisms of the control, particularly those control parameters that affect disturbance evolution and the system state evolution of the vehicle. And then when we analyze the car following behavior, we capture some key components by the AB model. And we also in this work, we developed a data-driven prediction model to be able to somehow scale up from microscopic to macroscopic behavior. And all these components here, they collectively impact the traffic-wide analysis. So let me move to the first section in our discussion here. So the first section is mainly we'll be discussing some empirical analysis of the car following behavior. So the main point we're going to make here is that we're using the asymmetric behavior model, and it's an effective tool to analyze these car following behaviors, specifically giving us some physical insights of the different behavior of these different algorithms and their effect on disturbance evolution. So a bit of an overview here. So the idea here is that in capturing these physical mechanisms for the car following behavior, we are using this AB model, which is an extension from the Newell's simplified model. So specifically, the use of this AB serves three main important features here. So one, although it might not capture all physical or details of the vehicle control, but it captures these key car following characteristics that matter at the traffic dynamics level. And most importantly, it is flexible enough to serve as a unifying framework to analyze different control algorithms, because here we're looking at MPC, linear controller, and eventually AI controllers. And also it can capture dynamics in car following behavior, so as we can gain like more direct insights into the disturbance evolution. So there has been some empirical studies on the AB model from Chen et al. In 2012 and 2014, but specifically these are mainly on human-driven vehicles. And this analysis on human-driven vehicles showed like two relevant reaction patterns. And the key point here is that it showed that this eta profile, or this component, this component eta, and its evolution throughout time, which we will call here a reaction pattern. And this reaction pattern is mainly describes this car following behavior. So two main reaction patterns or eta evolutions here are of interest. The first one is this concave reaction pattern, whereby, for instance, to describe this a bit, this eta starts as a constant parameter, and starts at a constant value. And if this eta equals to 1, this means that the vehicle is corresponding directly to Newell's car following behavior. And then, so when the leader undergoes some deceleration acceleration maneuver here, then we see that the follower here also deviates beyond that of Newell's. And when this happens, then the eta starts to increase, and we see an increase in eta beyond this value here, and it reaches a maximum value. After that, the recovery phase is in effect, and the car starts to decrease this gap between its leader. And this is when eta profile goes down. So this is in general what the concave reaction pattern looks like. And conversely, just a flipped reaction is something we call the convex reaction pattern. And it also has to deals with the evolution of eta through time. But in this case, if we compare it to Newell's reaction pattern, so when the leader vehicle here undergoes some sort of deceleration acceleration maneuver, what's happening here is the vehicle is the trajectory of this vehicle is shifted less than that of the Newell's trajectory. And what's really happening is that the eta profile is decreasing to a minimum value, and then a recovery phase happens to regain the gap, and it increases. So this is how the AB model captures our the car following behavior. But the main question is, and the main intuition here is that this is not what really we see in an autonomous vehicles, and we expect a bit more different behavior. So to answer these questions here, we do some empirical analysis. Mainly, we want to state if it is feasible to use this AB model to analyze the car following behavior of an autonomous vehicle. And here we want to answer these two types of questions. So can the AB model approximate these key car following behaviors under different control designs and control logics? And can it unveil physical control mechanisms, specifically those related to disturbance growth or disturbance decay? So the first type of experiment, or this is an experiment already available. This is, I believe, by Professor Dan's work group, and it's Stern et al. In 2013. So this is it's called Arizona control experiments, and available in the literature. So the setup here is an interesting setup of this experiment, whereby we have 21 or 22 vehicles, and we have one CAV vehicle. but the CAV vehicle was mainly instructed to behave just as a human-driven vehicle because actually there is a human inside it. And at some point, when there is a disturbances, the AV was instructed to maintain some desired speed to in an effort to dissolve the stop-and-go disturbance. So this is like an interesting type of controller specifically designed to alleviate the stop-and-go cycles. And so what we are interested in here is seeing if this AV model can capture this behavior of this specific type of control logic. And we can see from the figure on the right here that, so what's happening here is that if you look at the green leader vehicle velocity profile, it's undergoing an acceleration. Oh, and the blue profile is just shifted to account for the time till disturbance propagates. And then, so the acceleration, the velocity profile, the vehicle is accelerating and then decelerating and then accelerating. So what's happening in if you see at the red line here, the red line corresponds to the automated vehicle. And it's interesting what the automating vehicle it's doing is trying to keep a certain constant speed as to resolve this stop and go cycle. And how we can translate this behavior into the ETA model is something like this. So when the vehicle starts to accelerate, but the autonomous vehicle, the follower maintains a similar speed, we can see that there is a gap being created in this sense here. And we see that the ETA profile actually increases from a certain level and goes to a maximum value. And then when the leader vehicle starts to decelerate, also starts to decelerate, and the velocity profile, you can see this drops like this here. But the automated vehicle also maintains its speed because that's what the control logic is instructed to do. And we see that the gap actually decreases, and this is captured from the ETA model with ETA evolution with this decrease in ETA. And then things return back to normal. So in this case, there is a proactive mechanisms from the CAV, and we can see that the CAV is actually able to resolve the disturbances and really dampen all this stop and go disturbances. So in this case, we have a concave convex reaction pattern from our ETA evolution. Another second type of an experiment we analyzed here, actually this experiment is done by our co-author and by our collaborators, Professor Danjo Chen group. So in this experiment, the Lowell control experiments, we have two vehicles, one leader vehicle and one follower ACC vehicle. And the ACC vehicle was the lead vehicle was instructed to cruise initially. Here it's cruising and then reduce its speed and then accelerate back again. So it's a typical deceleration acceleration type of disturbance happening. And the ETA profile analysis here, it captures this reactive mechanisms of the ACC. So what we mean by reactive is that you can see that looking at this green and blue speed profiles here, is that when the leader drops its speed here, the autonomous vehicle, the ACC vehicle, responds but with a certain delay. And this delay is accompanied by a decrease in the gap between the leader and the follower. And this is what's happening here, that ETA minimum is decreasing during this delay and deceleration. And then similarly, what's happening is that when the lead vehicle starts to accelerate, there's also a reaction, but with a delay in reaction, and we can see this here. And this increases, and this is captured by an increase in ETA to a maximum value. And you can see that there is the disturbance here is prolonged, and the duration of the disturbance here is duration of this disturbance is much longer as the recovery phase is longer. And you can see this in this case here. And so the shape here that we see is a convex concave reaction type of pattern. So the key insights from our analysis in this case is that the AB model can approximate these key confound behaviors, specifically that we know that different controllers, as we saw, yield different response behaviors. And this can be effectively captured through the ETA T profile. And then the eta t can help us, or these reaction patterns can help us capture these underlying control mechanisms and the physical control of the vehicle. And then one also interesting figure is that the AVs differ significantly from the human-driven vehicles. You can see from the AV reaction patterns, they have some sort of a compound reactions, so which is different from what we expect in a human-driven vehicle. So having introduced all this, let's delve in more into analyzing these control mechanisms, and we'll focus in this section on the linear controller. And our aim is to really gain some physical insights, how this control mechanism acts, and what really governs its behavior. So to do this, we first look at just a typical linear feedback control structure, and we know from there's a lot of literature out there on linear controllers and linear feedback controllers, and they are quite out there being researched and actually used. So in this, we use a typical controller developed in our previous study, Zhu and An, in 2019. So the main idea here is that this is a hierarchical type of control. You have an upper level controller, which basically governs this car following behavior. And this is based on the sensor data it's being fed to. And the sensor data gives you data on relative speed and the distance. And when this upper level controller has this data at hand, it prescribes a demanded acceleration. But then this controller has a lower level design. So the lower level design, the main idea is to capture some uncertainty in the vehicle dynamics. And this is captured through the GLVD, the generalized linear vehicle dynamics equations. And after incorporating all this uncertainty, we have our acceleration demanded by the controller. So some key points we want to focus on in this upper level controller is that we have this desired equilibrium spacing. And this is a well-known concept, and it's based on the widely adopted constant time gap policy. And you can see that the constant time gap policy states that my desired spacing is a function of my velocity, and this parameter time gap, which is typically taken as 1 second or anything else. So it depends. So this is actually basically just like Noah's car following behavior. And this is how my desired spacing is computed, or what is my desired spacing. And then what I care about is what is the deviation from my target spacing. So what is the difference between my actual spacing from my sensor data and my desired spacing. And I also care about this relative speed, so the speed between a leader and its follower. And then the lower level controller, so just basic idea here is that it models the jerk. So the jerk is a function of my acceleration and my demanded acceleration. And you have two key components here. We'll not talk about them much, but these two components are on actuation lag and this ratio between demanded and realized acceleration. So what is really of key interest here, and what we saw in these linear controllers, is that the system state defined is really what matters, because this system state is what I care about, or what I'm trying to control in my control algorithm, or how does this system state is differing or evolving throughout time. And the system state is defined by these three components. First, the deviation from target spacing, my speed difference, and my acceleration. And then with a linear control law, or linear feedback control law, then it states that the controller the controller demanded acceleration is a function of this system state multiplied by a set of weights. So these weights, we call them control gains. And we have three of them essentially here, because we have three states. So the first control gain is relative to the deviation from equilibrium spacing. The second one is Kv, which is a feedback gain for the speed difference. And then the third gain is Ka, which is for the acceleration of the vehicle. So these are very important in our analysis of car following behavior. Why? Because they essentially denote this regulation magnitude for each component. So how much do I value this change in desired, this deviation from equilibrium spacing? How much do I value the speed change, or how much do I value a change in acceleration? So somehow these would prescribe how should I act, how fast should I act, and how strongly should I act. And this is why they govern this car following behavior. So now the question comes is, okay, what is the role of these control parameters and how can they regulate actually the car following behavior? And thus we are interested here in answering these 4 questions. So what car following behavior does each control gain trigger? What is the combined effect of these gains? And what is the range of possible car following behavior? And how would this translate into disturbance evolution and traffic impacts? So to do this, we designed a simulation setup, and really it's a simple simulation setup where we generate, create these synthesized least trajectories. They have this type of velocity profile, and these are created for different ki parameter settings. And then we want to extract the AV trajectories and estimate this eta evolution, essentially estimate the shape. We're interested in this eta min value, eta max value, and this reaction pattern, as we discussed before. So this is what we found is really interesting here. And the first part of this analysis is we want to see, so what is the observed impact of each of these gains alone? So I'm talking about Ks, Kv, and Ka. So what we did here is we have a leader profile here in blue, and then we have 3 different scenarios. The first scenario is where Ks is dominant, so the gain for regulating spacing is dominant, here seen in green. And the second is where Kv is dominant in yellow, and Ka is dominant. So concerning the first case where Ks is dominant, so the controller command really values a lot this deviation from target spacing. So what the controller tries to do is, okay, please maintain my target spacing. And what happens here is that it pushes it to just a noise behavior. And you can see this noise, it's plotted, maybe not seen too much, but it's this black dotted line. And when Ks really is dominant, then the controller is pushed towards this noise behavior. And you can see this is the eta profile. It's somehow constant around 1. But then in the second experiment, when I have a Kv dominant, and essentially what the controller values a lot here is to match the leader speed. So I want to eliminate this difference between a leader and follower speed. And what it does is really interesting. It generates a very responsive behavior. And we can see this from the trajectory is that whenever the lead vehicle starts to go with this deceleration, acceleration, oscillation, it responds really fast and really aggressive. And then this responsive behavior generates a concave pattern, a concave convex pattern. And we can see that this is captured here by this deviation beyond nulls. And then for the last case where Ka is dominant, so what this means is that the controller really wants to minimize acceleration, and it really wants to resist any acceleration change. And this is not a good behavior. Why? Because we can see, even this is an exaggerated case, but we can see that what the vehicle is doing, it's resisting any change in acceleration, and it becomes a really dangerous situation whereby in this case they crash. But you can see that the controller is not responsive at all, and it resists any change, and it only takes a reaction when really it is needed. And this is captured through a convex, concave type of reaction. So now we know how each of these gains work. Now we are interested on, okay, what is the collective, or how do these gains act together to govern the car following behavior? And so in here we analyzed a really vast number of trajectories, but we're gonna show this one here. Specifically, we'll focus here on the concave convex reaction pattern and try to analyze it and see what's going on. So in the first figure here, you can see the eta evolution. And then in the second component, we are looking at how each component in this equation here, which is specifically the gain and its respective state space component, So the distance, the speed, and the acceleration. And then here we look at the speed, relative speed profile, and then the acceleration. So what's happening here is that in this reaction pattern, the first thing is that there is a deceleration maneuver by the leader, and the controller perceived that, okay, there is something happening, and I need to invoke also a deceleration response. And because KV is really large here, and it has a major component in this controller, then there is a very responsive, it is responsive to this speed difference. And it has a rapid response. And this rapid response, what's captured here is through this concave pattern. And what's happening, if you look at the gains here at the blue profile, which corresponds to the this KV delta V component, it's really dominating in this case. And so you know that the controller is valuing this type of behavior, and it's responding really effectively. But at a certain time, the gap, what's happening here is that the gap between the leader is increasing. And at a certain time, now KS, which is regulating the spacing, KS kicks in and it tells the controller that, okay, I'm too much deviating from my target spacing, I need to go back. And it invokes a response here, and you can see like this KS and the bit KA start to come in play here. But then when the leader vehicle starts to accelerate again, so it's the next phase in the oscillation. Also, what's happening is that the controller invokes a responsive acceleration maneuver to catch up with its leader. And this catching up with the leader yields a convex pattern, because essentially I'm catching up and decreasing my gap with the leader. So in general, what we saw is that a higher KV value yields a stronger concave convex pattern here. So in a similar fashion, similarly what's happening in a convex concave pattern. So we follow the same logic, and logically what's happening is similar. But what we notice here is that this Ka component is what's driving this strong convex concave shape. Because essentially what's happening here is that when the controller invokes a deceleration response, it is not very responsive because Ka is dominating, and it's really resisting this controller to have any change in its speed or in its acceleration. So what's happening here is that the follower starts to decrease its gap between its leader, and this yields a convex reaction pattern. But then at a certain time as well, the Ks, which regulates spacing, also comes in play and telling it, okay, now it's dangerous, I need to retain my equilibrium spacing. So, and this, what's happening here is that the eta increases, and then we see a concave pattern here, essentially to recover in the recovery phase. And essentially also this is contributed to the fact that the controller is not very much responsive. So now what we care about is, okay, we want to see where are these two shapes located inside this as a relationship to these gains. So we saw that we have two types of reaction patterns. The first one is the concave convex. It looks something like this in red. And the second one is a convex concave. It looks something like this. So mainly the concave reaction pattern, it is present mainly in these high gain values, specifically when KV is high. So this is something we somehow expect, because when these gains are large, then we want to have a strong responsive reaction. And you can see that when KV increases, it really affects a lot this red region. But on the other hand, the green reaction pattern, which is a convex concave, it's really present on this lower end of the controller, lower end of the control gain settings, mainly small control settings. And we can see that this green area, it's increasing whenever we increase the magnitude of Ka. And I'm talking here about the absolute value magnitude. And this is because now the vehicle is less responsive, and we yield a convex concave reaction. So now what we want to do is we want to map these map these gains with respect to the AB control parameters, which mainly I'm looking at the eta min and eta max values in here. And we want to check how these values change with respect to the gains. So just to give you here some information, so in the first graphs, I'm looking at this relationship between Ks, Kv, and eta min. And here I'm looking at the Ks, Kv relationship with eta max. And here I'm looking at like Kv and Ka relationship. So in summary, what we noticed is that this eta min and eta max values are really monotonic, have a monotonic relationship with respect to Ks. So what this means is that whenever Ks increases, both of these values tend to go towards 1. So, and 1 means here that I'm going towards a null-like behavior. But when Kv increases, or Ka in a sense, there is a non-monotonic relationship. And in this non-monotonic relationship, if we look at this graph here, we see that when Kv is increasing, we have some sort of a flip in reaction. And this is mainly due to the fact that what's happening here is that if my Kv is increasing, I'm going from a convex reaction pattern. I'm going from this reaction pattern to this reaction pattern. So I'm having a flip in relation in a response behavior. So in general, what we saw is that this comparative strength between Ka and Kv determines this reaction pattern, while Ks works more as effectively dampening the reaction or moving it towards a null behavior. So now we interested ourselves in so how does this reaction patterns or how these control gains actually manifest themselves in a traffic level implication. And in the first experiment, we looked at just seeing if this vehicle ordering within this heterogeneous platoon actually has an impact or not. So we have two types of controllers. We simulate for 10 vehicles, and we have here 5 vehicles which are concave convex, and then 5 vehicles which are convex concave. So I know this might be a bit convex concave, but weird, but then I color coded them, so it's easier to follow. So in this sense, when we have in here we have 5 vehicles concave convex followed by these 5 vehicles, the green shape, and then we can see that the disturbance is being dampened. Specifically, it's more effective in this first part where we have a concave reaction pattern, while it is less effective in the last vehicles. But what's interesting here is that when we alternate these vehicles, meaning that we have a red, green types of vehicles, we see that the the disturbance actually is amplified along the platoon, and we have no disturbance dampening at all. And this leads us to think that vehicle ordering actually affects how this disturbance magnitude, the speed reduction. Essentially here that the magnitude is amplified, meaning the speed, minimum speed is decreasing throughout the platoon. So that this ordering actually affects and how this disturbance evolves from one vehicle to the other. But now let's look at what is the impact of this vehicle composition. So essentially, what is the impact of this reaction pattern? Either a concave convex or a convex concave. So in this experiment, what we did is we have 2 types of controllers. They are both concave convex. And what's interesting is that if we look at the speed profile of the platoon, we have really very effective disturbance dampening, and we can see the minimum speed is increasing. You can see it in this vehicle here, and we have really efficient disturbance dampening. And this is really more pronounced as we increase this Kv value, because you can see that for these first vehicles which have higher Kv value, we have a higher disturbance dampening. So this leads us to think that, okay, this concave convex reaction pattern is really interesting in disturbance dampening. So in the second experiment, what we did here is we have 2 types. The first is concave convex, the second is convex concave. But the average behavior here is expected to be concave convex, because these are the green vehicles were chosen to be around the boundary. So what we have here is still there is disturbance dampening, but it's less effective, especially with caused by these type 2 vehicles. But when we flip this scenario, and we have this average behavior here is dominated by a convex concave pattern, we see that there is an overall amplification of our disturbance, and the speed, minimum speed, starts to increase along the platoon. And this is essentially means that our platoon is really working. It's increasing or amplifying this disturbance. And then in this experiment, we really have all vehicles as convex concave, and we can see there is extensive amplification of disturbance. There is even some speed overshooting here, which creates a bit of smaller disturbances, and our platoon is working terribly. So some insights on this analysis here is that this curve-following behavior during disturbance is captured through this eta profile or eta evolution. And we see mainly two prevalent reaction patterns. We have a concave convex and a convex concave. And there's an intrinsic mapping between these control gain values and these eta t parameters from our AB model. So eta min and eta max. From a traffic level implication, we see that these convex concave patterns, they lead to disturbance amplification, while the concave convex, they lead to disturbance dampening. And in a mixed platoon, it's really important to see what is the overall composition of these vehicles, how much each type of reaction pattern is dominating, and this vehicle ordering plays an important role. So moving into similar type of analysis, but now we look at the model predictive control. And in the model predictive control, we really have a similar type of formulation, which is a wide known formulation. And the system state is basically the same, because essentially these are the important factors that we want to control and we care about. But in here, what the MPC develops a running cost function and the prediction horizon. And essentially what is most important, or what's significant about this MPC, is that it allows for this constraints to be put. So essentially we have constraints on acceleration, minimum acceleration, maximum, constraints on deceleration magnitude and acceleration magnitude, and even some safe spacing constraints and deviation from target spacing. So these play an important role, and we're going to discuss this moving forward. But what's interesting here is that we also have a QI matrix, which plays a really interesting role here. And this weight matrix is multiplied by this state factor, which essentially means that it is somehow working equivalently to our gains matrix in the linear controller. Essentially, the first component in QI works similar to QS, and it's a coefficient for the deviation from equilibrium spacing. And the second component is relative to the KV, and it's a coefficient for the speed difference. And then the third component is similar to that of the KA. So in a similar fashion, what we want to do is we want to check, okay, how these different control parameters in the MPC, how they govern this curve-following behavior. And in the first setting, we have an unbounded setting. So in this setting here, what I'm showing you is an unbounded setting in an MPC. And we have a similar analysis whereby we have a lead vehicle. We have a lead vehicle, which is in blue right here. And we have three different cases. The first case, it's one, this alpha 1 is dominant, which is similar to one, the controller really values the spacing or change in spacing. And what we see is that in this scenario, we have a really similar behavior where the controller is pushed towards null type of behavior. And we can see that the eta profile is closer to 1. And in the second parameter, and the second parameter, alpha 2, which acts basically similar to the KV, and it wants to regulate the speed and match the leader speed. And what this does is it generates a responsive behavior and a concave convex type of pattern seen here in yellow. And alpha 3 It acts also similarly where it wants to minimize the acceleration. I want to resist any acceleration change, and it yields a convex concave pattern here. And we can see that from the red profile, the vehicle tries to close into its leader more and more. So in an unbounded setting, the behavior, the car following behavior of an MPC controller is consistent with that of the linear controller. But what things comes more complicated or more interesting is when we have a bounded setting. And in a bounded setting, really, it's different between these convex, the behavior is different for different reaction patterns. So in this first setting, we focus on, we focus on this convex concave pattern. And what we do here is we analyze the acceleration bounds. So in the first set of figures here in the top line, we analyze the bounded acceleration setting. In the second case, we analyze the bounded, in the first case, the bounded deceleration. In the second case, a bounded acceleration. And in the third case, a compound effect. So what we do here is we bound the deceleration value of the follower. Essentially, what's happening here is that the leader is decelerating, but the follower decelerates, but then it has a bound on this deceleration magnitude, and it cannot decelerate beyond that. So what's happening here is really interesting, is that when this deceleration is activated, we have a significant convexity being developed. And this convexity is intuitive because we are now closer, because we want to decrease our speed, but we cannot, so we have this convexity being created. And this leads to a bit of instability in our control, whereby if we look at the velocity, the minimum speed is increasing beyond that of the leader. And we also notice here that there is a jerk increase, especially when there is a transition between the deceleration phase and the acceleration phase. So now in the second setting, where we have a bounded acceleration scenario, and we can see here that we bound the acceleration of the following vehicle. And what's happening is that in the acceleration phase here, we see that there is a significant convexity being developed, and this is really an increase in the gap, and it's prolonging this recovery period. So it's really having this effect on prolonging our recovery phase. And then we do have a bit of an overshoot in speed because the vehicle wants to close in the extra gap being created. And then when we have a compound effect, so when these two bounds are being activated, we have some sort of also a compound effect whereby we have a more convexity and much more concavity being developed. So there is also the disturbance duration is increasing and increasing. So in the bounding setting, but now we are looking at a concave convex pattern. So we also have a similar analogical type of behavior. But what's happening here is that when there's a bounded acceleration, we see that this concavity or this gap between its leader, it's a bit shaved off, and a convexity is being generated. And when we have a bounded acceleration, we also notice that there is an increase in the gap here. Eta profile has a concavity being developed. And the compound effect is also similar, whereby we have more convexity and more concavity. You can see this in the red profile here. So some insights into the MPC analysis we have shown is that in an unconstrained setting, the MPC car following behavior is consistent with that of the linear controller. And we have somehow an analogical mapping between these parameters that we care about in an MPC and parameters that we care about in a linear controller. And what we notice is that an active deceleration constraint leads to convexity during deceleration, while that of an active acceleration constraint leads to concavity, a bit of speed overshooting, and longer recovery period. So from a traffic level implications, we ran a bit of experiments, but we're not going to show a lot in here. It's still study in progress. But what we notice is that when enough vehicles have this deceleration constraint active, this may lead to disturbance amplification, because essentially I'm creating convexity, and convexity is somehow associated with disturbance amplification. And if I have enough vehicles with active acceleration constraints, then this may lead to an increased duration in disturbance and create possibly more smaller disturbance. So finally, I will go shortly in this section whereby we developed this prediction model for the car following behavior. Essentially, we're using here a convoluted Gaussian process. And so the main problem comes here is that, so if I'm given a control paradigm, a linear or an MPC or any other control paradigm, and I'm somehow able, I know the physical behavior and I know what are the control parameters that govern this physical behavior, and I can understand this physical mechanisms that's happening. So given this control paradigm and given this control parameters, and for different leader information, what I mean by leader information is oscillation, different oscillations. For example, deceleration, acceleration magnitudes, and drop in speed, and so forth. So the question becomes, can I predict this car following behavior? And this is really important in efforts to connect this microscopic AV control to the macroscopic traffic impacts. So what this problem boils into is the fact that we want to build this eta profile. So given this information, I want to somehow build an eta profile. And this means I want to predict this eta min and eta max values. And I want to see which reaction pattern I'm dealing with. So I want to predict these two components. So we did this in our approach. Basically, our modeling approach uses a multivariate Gaussian process. So the main, the nice use of this model, or the main components here, is that what we want to do is, this is a dynamic process and it's changing throughout time, and there is some innate correlation in this response. So we want to predict this eta min, eta max, while addressing this innate correlation. And for this, we use this MGP model, multivariate Gaussian process, because it has a Bayesian interpretation. And this gives us uncertainty measures, and it allows to model these two components in a Bayesian interpretation manner. And this is really beneficial if we are to scale this aggregate towards a traffic level impact, because we really we care about how much certainty I am on the prediction models, on my prediction values, and this uncertainty parameter is really of key interest. So in our controller, what this prediction model does is it takes a set of inputs, which basically are the control gate parameters and some parameters relative to the leader oscillation being happening, deceleration, acceleration, and velocity drop, and it predicts this eta min and eta max value. And we also couple this prediction model with a logistics classifier type of prediction. And what this does is it predicts the reaction pattern. So it essentially tells me if I have a convex concave reaction pattern or I have a concave convex reaction pattern. And using these two coupled together, what essentially we achieved is we build this eta profile. So for the sake of time, I will move into concluding here. So some conclusions about our talk here is that so these physical mechanisms of the control is really an important topic to analyze and really understand how these behaviors and what are the key parameters that we want to focus on, and how these translate in traffic level implications. And this is useful, and this is captured through the AB car following analysis framework. And when we were discussing the linear controller, we saw that this disturbance or disturbance evolution is captured by the eta t, specifically by the reaction patterns. And we have two dominant reaction patterns, concave convex and convex concave. And then there's an intrinsic mapping between the control gains and the shape of eta and its parameters. And when we talk about the MPC controller, we saw that in an unbounded setting, the MPC control mechanisms are consistent with that of a linear controller. And what plays a role here, or what really impacts the behavior, is these constraints when they are being active and how they can alter really the reaction pattern. They can increase our convexity or increase our concavity. And then we talk about disturbance propagations. We talk about traffic level implications. we see that generally a convex-concave pattern leads to disturbance amplification, while a concave-convex leads to disturbance decay, which is really useful. And then these constraints, they can lead to either disturbance amplification or a prolonged disturbance, and these are of key importance to us when they are triggered. So part of our ongoing and future work, as I said, this is part of a series of work. This analysis is part of a series of work and part of like a multiple ongoing process. And so currently we are developing the new prediction models, which essentially this prediction model predicts the eta evolution with its timings as well. So we are interested not only about the eta min and eta max values, but when do they occur, and after how much the time, I mean that once a disturbance occurs, after how much time can I anticipate a drop, anticipate a minimum eta or a maximum eta. So this prediction of these timings are really key here. And then we're studying multiple interactive disturbances, and we're analyzing AI-based controllers in a similar framework, in this unified frameworks, but really gain insights on their actual behavior. And we haven't dealt much with connectivity and other types of parameters that can be incorporated in our analysis, which means here like some different control settings, different paradigms, and different platoon compositions and different settings. So this is, I will not go through the appendix, but this is for this. So this is the end of my topic. I thank you a lot for your attendance and for listening. And please, if you have any questions, suggestions, and concerns, I'm happy to look at it. I think I'm a bit maybe over time. I apologize for that, but there were a lot of stuff to cover.
That's fine. Yeah. Thank you for your interesting presentation. So everybody, if you have any questions, you can unmute yourself, ask it here, or write it down in the chat section so I can read it to Wissam.
Hello,
Hi.
good morning.
Yeah.
May I ask a question?
Yeah, please go ahead.
Hi, good morning. My name is Wen Longjian from UC. I'm sorry I was late. I thought it was 11 a.m. in our time.
Nice to meet you.
So I would like to ask one quick question. I noticed that you examine the model control has a bounded acceleration, bounded deceleration, and I'm wondering if you check if the model is still safe, is collision free, and
yeah. So on this set, yeah, that's a good question actually. So in our settings, so in an MPC formulation, because you have this optimization framework and this feasibility is always important. So we want to get a feasible solution. And in this case, when the control, this acceleration and deceleration are triggered, in our setting, we make sure that we do have a feasible solution and it's safe, and we still have our safe spacing, and that is actually a feasible solution.
Okay. So, yeah, maybe as a follow-up, I noticed that you done a simulation. Is that possible to analytically, mathematically prove it? Because if we ever want to implement it, we want to have a high, very, very, almost kind of a mathematic guarantee that is the best situation.
Yeah.
Is
So
that possible to mathematically prove that you really satisfy all this nice properties?
Yeah. So concerning MPC, as you know that, so proving, guaranteeing stability, guaranteeing stability in a linear controller is actually doable. We can guarantee stability. But when we discuss this MPC formulation, stability guarantees are a bit harder. But if we, from this paper here from Zhu and al paper in 2019, developing this MPC controller, they proved some generalized like stability solutions, but this is only mathematically derived for certain scenarios and for certain applications. So I would refer you to this paper. It has a mathematical proofs on these derivations of the stability analysis.
Okay, thank you very much. I got to run for another meeting. Yeah.
Thanks a lot for your question.
Hey, hello. This is Shao from University of South Florida.
Nice to meet
you. Thank you for the nice presentation. You said you have concave and convex and convex concave patterns. So I just wonder if that is correlated with reaction time. I did not see a reaction time term in your model, but if you allocate different reaction times, you could see different concave and convex patterns. That's what I'm guessing. Yeah.
That's.
And also another question is the concave convex pattern not just like fixed behavior for each individual? Does it also depend on the preceding vehicle's trajectory? For example, if it's a deceleration, could be more likely to be a concave convex, or its acceleration is more likely to be convex or concave, or the other way around. I'm not certain. I have these two questions. Thank you.
Yeah. So concerning the time varying response, so definitely these reaction patterns are dependent on these different time gap. Specifically, we're looking at this time gap pattern here. This time gap parameter here, and it has a really big impact. And this time gap parameter can change our response variable, concave, convex, and essentially changes the magnitude of these two different shapes, but the shape is still preserved, and we see those reaction patterns. But somehow the magnitude of it is definitely dependent on what is the reaction response time here. And I would also like to add here is that so in the lower level designer, when we're controlling for uncertainty, we have this really important parameter. It's called actuation lag. So this actuation lag, we delved a bit into it, but we didn't give a full analysis on it. But this actuation lag is somehow this lag in response relative to uncertainty when seeing. And this is a very key component, because if the actuation lag is large enough, what happens is that there's an oscillation happening, and the vehicle cannot respond in time because it's delaying its response. Somehow it's not responding well because there's some uncertainty. And what's happening is that this oscillation somehow gets compounded and compounding, and we have a really much worse performance. And in this case, we expect that like the convexity to increase a lot, and maybe the shape might differ, but we have a really bad situation where there is no stability at hand. Yeah.
Yeah, thanks. I mean that whether the concavity depends on the vehicle's trajectory.
Yeah, so the concave, so these concave and convex patterns, they are mainly relative to what the leader is doing. So they change with this leader trajectory, they change with this control settings, but they are not really a function of what is the second vehicle is doing. They are basically a one-to-one relationship between the leader and the follower itself. And to expand on this, what we are looking into more is this concept of connectivity, because from a linear controller, you can have also feed-forward gains. So essentially, you're feed-forwarding your acceleration values or what's happening with this following vehicle, and you're feed-forwarding it across the platoon. And this really has a major component and impact here, because now this reaction pattern is not just dependent on what's happening with the leader and the follower, this coupled relationship, but also with information coming from across the platoon.
All right. Thank you. Yeah, thank you, Wissam. That's great.
Thanks a lot, Professor. Thank you.
So I have a couple questions.
So
why do you think these concave convex patterns arise? Is there a physical explanation? It's related to the controller, right? The fact that it's linear, maybe. I'm trying to guess, but maybe you said it. So what's your...
Yes. So these definitely arise on so in this specifically these are relevant to the system state. So they arise on how are we responding to these disturbances coming from the leader. So a leader undergoes a certain disturbance, deceleration, then acceleration, and then what's happening here is that we are responding to this deviation from target spacing and responding to these oscillations with a certain magnitude. And when we respond, and when this response actually to this deviation is captured through a deviation from null spacing or deviation from null trajectory, which is captured from the eta profile. So essentially, when I'm increasing the gap, I'm having a more concavity, and when the gap between me and my leader decreases, I have a more convexity. So this is like how the system state evolution is evolving throughout time. It's similar to how this eta t parameter is evolving throughout time.
But a physical explanation, because I think it's just like an error. So before it overshoots and then it undershoots, it's like converging in a sine wave pattern, maybe, to the neural trajectory. Just kind of going up and down.
Yeah.
I don't know if you've seen more than one cycle. Here you showed, but maybe you have like a sine wave, right? That keeps getting smaller.
So in these simulations, we have only one cycle, but in the empirical analysis, we have multiple cycles, and we see this eta increasing, decreasing, increasing, and decreasing, and specifically, it's some sort of disturbance description.
But is it converging when you say you observe multiple patterns?
Yes, it converges. You mean like it goes back to one? So
Yeah. So to me, the explanation is that the linear controller is not perfect, right? So
yeah,
it's kind of an error that it's trying to converge, right?
Yes, definitely. It's the linear controller is very much prone to error, and we can see that. So when we have it can really in these settings here. So an error, these linear controllers can have, if you see at this velocity profile here, it can actually amplify this disturbance when it tries to copy it from vehicle to vehicle. And we can see that this eta profile, the speed profile here, it has an overshoot at the end. So it's creating actually, this linear controller is actually, when it's trying to converge, it can create actually disturbances along the way.
Right. And also you showed a figure where you stop the game. There's a figure where you you can't hear me?
No, I can't hear you, sorry.
So it was where one parameter is dominant and you show that it converges to the Newell trajectory?
Yeah, let me... This one here?
So wouldn't that be a solution to all our problems? And by problem, I mean, diminish the string instability of these ACCs.
Yeah, that's a very interesting question. But essentially, so in some sense, you actually want your controller to behave in a concave convex pattern, because you want to make sure that you are effectively dampening our disturbances and maybe not just reacting similar to logistic behavior. We want to effectively damping, and if we want to achieve this, essentially this is one type of achievements for the autonomous vehicles. They are effectively able to dampen our disturbances, and this effectiveness and dampening disturbance is related.
So you're saying that with the convex concave, you can dampen in any
concave
situation?
Convex. Yeah, in a concave convex pattern, and this yellow pattern here, you can achieve an effective dampening of disturbances, even for really pronounced disturbances.
Right, but you overdump, right? But yeah, I mean, I think this is a great direction because indication of how to set these parameters if you want to limit strings, right?
Exactly. So this raises a very interesting question, and this comes a problem on, so what is the sweet spot here, right? So what is the sweet spot between achieving a good throughput, achieving a good stability, and achieving a good, this sort of sweet spot? And this is something we're trying to, and this is something we're trying to achieve here by analyzing these control parameters. Because essentially what we can achieve is that, so I don't just want to put these parameters arbitrarily just to have string stability. I want to put them in a way that I'm effectively dampening disturbances. I'm achieving some sort of a traffic level advantages from throughput, from stability, and from all this stuff. So there comes this sweet spot of these parameters whereby I need to really pick them the right way.
Yeah, really, really interesting. Do you know if the original work of Stern et al., they found something similar or related?
So in this work, so you mean from reaction pattern shape? So in this work, what we mainly use are their field type analysis. But the main interesting point here is in their experiments, they have a really just a specific control logic. So their control logic is just to dampen this stop and go disturbance, and they do it by putting this average speed. But really, if you look at this case, somehow you can say that if this is the control logic, it might not be very, very much effective. Why? Because if I put my speed as the average speed, I can create a lot of gap between the leader. I can really increase the gap between the leader, and this might not be some optimal controller to design.
Yeah, that's like over damping, right?
Exactly, yeah. So you're creating this really large gap.
All right. That was awesome. Thank you very much. Do we have any more questions? I guess we went really overboard, but
yeah, sorry for that.
I guess not.
Yeah,
so
there's yeah, go ahead.
Yeah, go ahead.
I'm just saying that there's like a series of other works on here, and we're expanding more on this analysis, and hopefully we can share with you sometime soon.
Yeah, excellent. Good to see your co-author, Swan, there.
Oh,
really nice work. Congratulations.
Good to see you, Jorge. Yeah. Great job, Wissam. He's the one who did all the heavy lifting.
Excellent. All right.
With your guide.
All right, so I would like to thank everyone for coming today, especially the speaker. All right. Thanks very much again, and hope to see you all soon as soon as we get more speakers. All right.
Thanks. Thank you a lot.
Thank you.
Looking forward.
Bye,
Thanks,
bye.
everyone. Thank you.
Thank you, Wissam.
Thank you. Let me stop sharing.